Hello everybody. This is the session how to solve design challenges on interfacing Ethernet PHYs with application processors or microcontrollers. My name is Thomas Mauer and I am a system engineer in the SEM group responsible for factory automation and control. We start with an introduction and then we look at three different parts. The first part is about Ethernet design fundamentals. The second part, we are looking at a specific TI reference design where we have an integration example with the AM5728 processor with the DP83867 Ethernet PHY. Then in the last part, we are looking about Ethernet PHY integration comparison between the TIDA 0110 and the standard AM5728 EVM. We conclude with a summary and outlook. There are different design challenges with Ethernet PHYs using processors. One of them is what kind of multi-protocol industrial Ethernet do you want to use? These protocols typically require two Ethernet ports. Then in your application you may have a standard Ethernet for an uplink, for an edge or cloud connection, or for configuration and diagnostic data. Next is what kind of Ethernet speed do you need? Do you need 10 megabit, 100 megabit or gigabit Ethernet? Then followed is the MAC to PHY interface. So here we have MRI, RGMRI and so on. Next is Ethernet topology. Now you can have a ring, a line or a star topology. And the last one is the new evolution for industrial Ethernet. This is, for example, T1, which is single twisted pair Ethernet for industrial, or it can be power over data line, which is also meant for POODLE or APL or PoE. Part 1: Ethernet design fundamentals. We look first at common Ethernet PHY terminologies. An PHY, which stands for Physical Layer Transceiver Device, provides a way to transfer digital data from one node, which could be a processor, an FPGA or an ASIC, to another node via analog signaling over either copper or fiber optic cable. There are three important processes a PHY needs to handle. First of all is the PCS layer, which stands for Physical Coding Sublayer. Then there is the PMA, the physical medium attached, and last the PMD, which is the physical medium dependent. There are other key terms and functions. One of them is MDI, which stands for Media Dependent Interface. So this is the TD or RX data lines. Then there is the MII, which stands for Media Independent Interface. Those are the digital pins between the processor and the PHY, typically the receive and transmit lines. Then there is start of frame detection or SOF, which is required for timestamping. A feature which needs to be in the PHY for many of the industrial Ethernet protocols is the fast link down detection. In this mode, typically the PHY can detect a link down in less than 15 microseconds. Last is cable diagnostics, which is TDR or link quality. Let's look at the connection between the PHY to a MAC, and this is a typical application circuit. So in the middle you see the Ethernet PHY. To the left side you have the MPU, CPU or FPGA, and it's connected over the MAC interface. And here I listed a few of them, which is from MRI, RMRI and so on to SGMRI. Then above it you have the SMI, which stands for Serial Management Interface. This is an out-of-band signal which is typically used for configuration data. On the right side you see the magnetics followed by the RJ45 connector. Below you have the clock source, which could be a crystal or an oscillator, and the status leads, which typically provides indication of link and activity. we are now looking at the MAC interface, which is used for the data transfer between the PHY and the MAC. The first of them is the MII, the Media Independent Interface. You see that this line requires a pin count of 15. So 15 pins are required in order to transmit data. And it supports the clock speeds of 25 MHz. This is for 100 megabit per second, an Ethernet link, or 2.5 MHz for 10 megabit per second Ethernet link. I've also listed here the pins that you need, and you need for transmit pins the transmit data, which is 4 pins, TX enable, TX clock, and for the receive pins you need the receive data, which is 4 pins, receive data valid, receive error, collision, CRC, and clock. Next is the Reduced Media Independent Interface, the RMII, which only requires 9 pins. And here you have 50 MHz for 10 and 400 megabit per second. And the transmit and receive pins are reduced. Next is the Serial Network Interface, which then only needs 7 pins. So here we only have 10 MHz for 10 megabit per second. So this is a legacy interface which you will not find on many of the newest PHYs. Now we are looking at the GMII, or Gigabit Media Independent Interface. This requires now a pin count of up to 24 pins. And here you have a clock speed of 125 MHz for the 1 gigabit transmission link. You see that you need here 8 transmit data lines, then transmit enable, clock, another clock, and an error signal. For the receive lines, you also need 8 receive data lines, receive data valid, error, collision, CRC, and clock. Next is the RGMII, the Reduced Gigabit Media Independent Interface. This only needs the half of the pin count of the GMII, which is 12. Here again you have 125 MHz for the 1 gigabit per second. Here you only need 5 pins for the transmit data lines, as well as the TX enable error and the TX clock, and for the receive the similar. The last in the list is the SGMII, or Serial Gigabit Media Independent Interface. This only needs a pin count of 4. And here you see that the clock speed goes up to 625 MHz. Here you have 2 differential lines, one for transmit and one for receive. Next we look at the Industrial Ethernet MAC and the frame processing. The MAC, or Media Access Controller, is typically for industrial. It's a 3-port switch. And you see on the right side, you see a picture. It has 2 physical Ethernet ports and 1 host port. Typically, this is a specialized MAC which is required for following frame handling methods. The MAC requirements depend on the industrial Ethernet protocol and if it's a master or a slave. So next we will look at the frame processing methods. First of them is the cut-through. This is received the Ethernet header, performs header analysis, and takes forwarding decision. Here the frame is not modified by the MAC. Examples for this kind of frame handling is Profinet, Ethernet IP, PowerLink, Sercos in the UCC or NRT channel, and typically you have here a delay time inside the MAC of 3 to 4 microseconds. The next is on the fly. Here the frame is forwarded to the second Ethernet port. The MAC can perform read and write access to the frame while it runs through the MAC. The CRC is updated at the end to reflect the frame modifications by the MAC. Examples for this protocol is EtherCut or Sercos when it receives Sercos frames. Here the delay time inside the MAC is typically below 1 microseconds. The last frame processing method is the store and forward method. This is typically a legacy mode used by the standard Ethernet MACs, which is store frame in the memory, perform header analyzation first before taking forwarding decision. The frame is not modified by the MAC. Here the delay time depends, and it depends on the length of the frame. For a 65 byte frame, the delay time is 6.7 microseconds, but for a 1500 byte frame, the delay time is 125 microseconds. Next is part 2 with an integration example of the TIDA 0110, which is the Citara AM5728 processor with a DP83867IR Ethernet PHY. Let's look at the system block diagram. On one hand, you have the AM5728 application processor, which has an inbuilt 2-port gigabit Ethernet switch. It's also referred as GMAC. It's connected over the RGMI interface to the Ethernet PHYs. One Ethernet PHY is providing the clocking for the second Ethernet PHY. Then we also have a power supply of 12 volt, which is provided into a PMIC, as well as into a DC-DC converter, and it provides then the three voltages of 3.3 volt, 2.5 volt and 1.0 volt for the two Ethernet PHYs. This is providing the top and bottom PCB view. On the left side you see the two Ethernet MACs. On the right side you see the bottom of the PCB. Here we see the Ethernet PHY PCB section. You see here the two DP83867 Ethernet PHYs just below or just next to the RJ45 connector. You see here the Ethernet PHY example when you are designing the schematic. On the top you have the voltage supply, which is 1.1 volt, 2.5 volt and the VDD-IO, which is 3.3 volt in many cases. Note also here that this is a device which is using the 1.1 volt, where our design, the TIDA 0110, is using 1.0 volt. Then on the left side you have the RGMI interface. Below that you have some strapping options. Then you have the SMI, the serial management interface, which consists of the MDIO clock and the MDIO data. You have the clock out. Then make sure and look into the datasheet that you are choosing the correct resistance for the R bias. And then you have the MDI interface. Here we have also EMI, EMC protection diodes. Now we are looking at the power generation. From a 12 volt, which is fed into a DC-DC converter, we are generating 3.3 volt. The 3.3 volt are provided to the Ethernet PHY. This is the VDD-IO. Next, this 3.3 volt is also injected into the PMIC device, and there are two available switching outputs. One of them provides the 2.5 volt and the other one provides the 1.0 volt for the Ethernet PHY. The bootstrapping pins are quite important for the Ethernet PHY. They are configured through Bootstrap during power on reset. The examples are MDIO address, full duplex mode or RGMI mode. On the DP83867 they exist in 4 levels. Level 1, which is 0 volt, stands for mode 1, 1.4 volt is mode 2, and note that this is a mid voltage level. Then 2.4 volt, which is mode 3, and this is also a mid voltage level, and 3.3 volt, which corresponds to mode 4. Note that the AM5728 should not get exposed to mid voltage level during power up, because this has an effect on the power on our lifetime. So you have two options when you're working with the bootstrapping modes with the DP83867 and the AM5728. Option 1 is configure only mode 1 and mode 4 and avoid mode 2 and mode 3. So this can be done because you can configure after power up over MDIO the PHY. Or the second option is that you add an isolation between the signals of the AM572 and the DP83867 while the devices are powering up. For the clocking and reset generation, you need to be aware of the following. We are using one crystal which is provided into the first Ethernet PHY. And then we are using the clock out signal of this first Ethernet PHY and provide this 25 MHz to the second PHY. In order to achieve this, we need to reset the two Ethernet PHYs individually. And for this one, we are using two GPIOs. So this is what you need to take care about. So port 1 of the Ethernet PHY, which is shown above, is providing a clock, which is shown here as XI. So we need to release the reset of the first PHY when this clock is active. Then it takes some time from this first PHY until a clock out is produced. This clock out is then provided to the second PHY. So note that we need to keep the second PHY in reset, and only once we have a valid clock, the second PHY can be released from the reset. Now there is part 3, the Ethernet PHY integration comparison between the TIDA 0110 and the standard AM572 EVM. This slide provides an overview between the DP83867 and the microchip or micro device, the KSZ9031. The DP83867 is part of the TIDA 0110, where the KSZ9031 is part of the EVM. We will not look at all the items or all the parameters, only a few. The current consumption in the smaller package is with the DP83867 lower than with the KSZ9031. Note also that the voltage generation with the KSZ1931 per the datasheet of this device can be done with an external P-channel MOSFET. This is to generate the 1.2 volt. Note that if you're using this option, that you are burning up to 441 milliwatt over the MOSFET. We will look also at the PCB and BOM area in the next slides. This slide shows the power supply solutions for the TIDA 0110 and the KSZ9031. This is on the right side, where you see that the TIDA 0110 is using the PMIC to generate the 2.5 volts as well as the 1.0 volt. The PMIC has an integrated DC to DC converter, which is quite efficient. Note that the KSZ9031 provides a solution to use an integrated LDO controller and an external MOSFET to generate the 1.2 volt from the 3.3 volt. This requires a lot of current consumption to be burned inside the MOSFET. So there are also some alternative solutions in case you don't want to use the PMIC to generate the 2.5 volt as well as the 1.0 volt, which is documented in the TIDA reference design guide. Now we are looking at the clocking. The TIDA 0110 uses a daisy chain clocking approach. This means that there is one crystal which is provided into the PHY 1, and then the PHY 1 provides the clock for the second PHY. This is done via the clock out pin. So it's configurable to provide a 25 MHz clock output. Note that the KSZ 1931 does not support this 25 MHz clock out, therefore you will need two clock sources, while with the TIDA 0110 you only need one clock source and then you daisy chain the clocking. This slide shows the layout area between the DP83867 and the KSZ 1931. On one hand, you see that the DP83867 solution has integrated termination resistors between the MRI interface, or which is actually the RG-MRI interface. You also see on the bottom side of the KSZ 1931 solution the two MOSFETs, which are quite big, and those MOSFETs are not required in the DP83867 solution because we are using here the high efficient power management IC with the integrated DC to DC converters. You can get started today using the following reference designs. First of all, there is the TIDA 00204, then there is the TIDA 299, 207, as well as a link to the DP83867 RG-MRI Linux drivers. If you are looking for a 10, 100 or 1 gigabit Ethernet PHY solution, you can refer to the AM5728 with the DP83867 reference design page, which you can find under TIDA 0110 reference design page. Thank you for attending this training.